Hi. In this video, we are going to continue our discussion of matrix inverses, focusing on the relationship between the matrix inverse and Gaussian elimination, culminating in a tool that we can use to calculate a matrix inverse whenever it exists. Let's start our discussion with just an overview of what we know about linear systems and singularity and non-singularity. For a system of n equations in n unknowns, that is a linear system with a square coefficient matrix, we've already discussed how, if A is non-singular, the system has a unique solution that can be given by the use of the matrix inverse, the inverse times the right-hand side. And if the coefficient matrix is singular, the system either has no solution or many solutions, depending on what the right-hand side is. We also know that we can use Gaussian elimination to solve for the unique solution when one exists, and to determine whether there is a solution or is no solution or many solutions as it may be, which suggests that there may be a relationship between Gaussian elimination and the matrix inverse. They are answering the same questions. When we have, so let's dig in a little bit to Gaussian elimination, remind ourselves of how this works and the key points of it. We start with a system of m equations in the general case, in n unknowns, and generate an augmented matrix with an extra column compared to the coefficient matrix. If, when we carry through forward elimination, we ever get to a place where there's zeros everywhere in a row except for the last column in the augmented matrix, we know that there must be no solution. That corresponds to a 0 equals something that isn't 0, inconsistent equation. If forward elimination ends up giving us less than n non-zero rows, then some variables must be free variables. Each non-zero row gives a pivot. If not every variable is a pivot, then some must be free variables. When there are free variables, we have infinite solutions. If forward elimination, on the other hand, gives exactly n non-zero rows, every variable is a pivot, and in that case, we know we have one unique solution. We can get that through back substitution. In the special case where we have a square coefficient matrix, n linear equations in n unknowns, the same basic rules apply. No solution, a singular system, occurs when forward elimination gives at least one row with zeros everywhere in the coefficient block, a non-zero only in the last column. Many solutions also corresponds to a case where forward elimination gives at least one row with zeros everywhere in the coefficient block, but also in the last column. Right? Why does this look similar to the previous case? Well, when we have exactly n equations, a 0 row leads to there being less than n non-zero rows, obviously, and that's the condition that we need in order to have many solutions. So we must have some 0 rows in a square system in order to get many solutions. Contrary to that, the case where we have one unique solution, that is a non-singular system, occurs only when forward elimination does not give any 0 rows in the coefficient block. That is, after forward elimination, we have exactly n non-zero rows. This already answers part of the puzzle. The existence of a 0 row in the coefficient block of a row echelon form is both necessary and sufficient for classifying a system as singular. We can identify matrix A as being singular, a coefficient matrix as being singular, by applying Gaussian elimination and at seeing that we get a 0 row in that block. Okay. Now, what about non-singular cases? In a non-singular case, we have 3 equivalent statements that we can make. There are exactly n non-zero rows in an echelon form. Every variable is a pivot. There are no free variables. So all sort of imply each other. We also know that in this case, back substitution leads to a reduced row echelon form that has a very special form. Every variable is a pivot. In the reduced row echelon form, those all have to be 1s. So we have 1s along the diagonal. There are no free variables. And so the fact that in a reduced row echelon form, the pivot is the only non-zero entry in its column. If there's no columns that aren't pivots, everything else will be 0. We'll have 1s on the diagonal, 0s everywhere else, except for the last column. So in the coefficient block, and it's a square coefficient block. So what does that correspond to? That is the identity matrix. The coefficient block of the reduced row echelon form of a non-singular system is the identity matrix. And we'll see that this idea that non-singular systems lead to the identity matrix is a key part of how we find matrix inverses. Okay. The next piece we need to make the connection between Gaussian elimination and matrix inverses is the idea of elementary matrices. We've discussed previously how each step we take in elimination, both forward elimination and back substitution, can be expressed in terms of these 3 elementary row operations: adding a scalar multiple of a row, to another, multiplying a single row by a scalar, or exchanging 2 rows. And any other manipulation we might try to do, we can actually express as a combination of these. Each of these operations, it turns out, can be equally achieved through matrix multiplication by a special sort of matrix called an elementary matrix. These elementary matrices are generated by applying this operation to the identity matrix, and once we have them, we can do these row operations, we can perform these row operations simply by multiplying by the matrix. The 3 classes of operations give 3 classes of matrices, although there are many individual matrices within each of these classes corresponding to different choices of I and J, different choices of K, and so on. Now, before we go into more discussion on elementary matrices, I want to take a brief interlude to discuss the concept of block matrices. Block matrices are going to make much of the discussion moving forward, both for matrix inversion and also for LU decomposition and some material later on, a lot easier. We're not going to go into this very deeply, but just introduce the basics. A block matrix is simply a matrix whose elements are other matrices rather than scalars, and they can be actually expanded into regular matrices, but we simplify our representation of them by describing the elements as matrices. As an example, I can construct a matrix M out of 4 matrices, A, B, C, and D, as long as I'm very careful to make sure that the sizes all match up properly. A and B have to have the same number of rows. I've indicated that here as P. C and D also have to have the same number of rows. I've indicated this Q. And the total number of rows in M is the sum of those P's and Q. A and C have to have the same number of columns, R. B and D have to have the same number of columns, S. and the total number of columns is R plus S. All right. We've already seen augmented matrices, or block matrices. The augmented matrix is one of these. It's a block matrix whose first block is the coefficient matrix, and second block is the column vector of the right-hand side. These both have the same number of rows. They match the rule. And this is a simple block matrix, but still a block matrix. Why do block matrices help us so much? Well, because we can perform operations with them in much the same way we can with normal matrices, just replacing normal addition, or scalar addition and scalar multiplication with matrix addition and matrix multiplication. All right? Again, all of the blocks have to be sized appropriately for this to work, but as long as the sizes are correct, the following kind of logic applies. If I have a matrix, block matrix, A, B, C, D, and another block matrix, E, F, G, H, the product can be found by taking the matrix product of A and E plus the matrix product of B and G for the first block here. Right? This looks exactly the same thing as we would do with regular matrix multiplication, walking along a row and along a column, but we're applying this to the block matrices. Right? The same thing for the second entry of the first row, walk along the first row, the second column, A times F plus B times H, and so on. In order for this to work out, of course, the sizes have to be correct, so these matrix multiplications are well defined. The number of columns in A and C have to match the number of rows in E and F, so that AE, CE, AF, and CF are well-defined products. The number of columns in D and B and D must match the number of rows in G and H, so that BG, DG, BH, DH are well defined, and so on. Right? But as long as we're careful about sizing, block matrices can really simplify the amount of writing, the amount of algebra we need to do to manipulate matrices. We are typically going to be using very simple block matrices, very often row block matrices like the augmented matrix, where we only have matrices aligned along a row. Okay. Why did we take this interlude? Because I'm going to start off using a block matrix to help introduce the idea of elementary matrices, to expand on some of their properties a little bit. Consider the block matrix consisting of two blocks, a matrix A and an identity matrix of the same size. We'll consider A and I to be, consider A to be square, or at least have the same number of rows as I. Either way you want to think about it shouldn't limit your understanding here. Multiplication by a matrix would give E times M is E times this block matrix, and the rules of block matrix multiplication mean that this E is propagated into each block, E times A, E times I. Of course, E times I is just E, so the product of this with this block matrix has EA and E in the two blocks. Now, if we apply some row operation to M, because A and I are lined up in a row, the rows of A and the rows of I sort of are continuations of each other in this larger matrix. If we apply a row operation to M, we must be doing the same row operation both on A and both on I, because we're looking on a whole row of the matrix M. We can represent this. R acting on M is equivalent to a block matrix of R acting on A and R acting on I. Now, this is where we can sort of make our first important connection. If E times A gives the same result as R times A, right? Then it must follow that E, which would be found if we applied that same matrix multiplication to this block matrix in the second block, must be the same as Ri, which would be what we find if we applied that row operation to that block. Right? In other words, the matrix that we need to achieve this row operation must be the matrix that we get if we apply that row operation to the identity matrix. We generate an elementary matrix simply by applying the operation to the identity. Okay. Let's go through a couple of examples to illustrate how that works. Right? Let's start with row exchange. An example row exchange elementary matrix is found by starting with the matrix I and exchanging two rows, say row 1 and 2. Exchange row 1 and 2 as here. If we applied that same row operation to a matrix A, like here, upper corner was 0, we need a row exchange to move the pivot upwards for Gaussian elimination, for example. That row exchange would take the second row and make it the first row and make it the second, and so on. Right? Now what we see is if we multiply this E by A, E times A, what do we get? 0 plus 1 plus 0 is 1. 0 plus 1 plus 0 is 1. 0 plus 1 plus 0 is 1. What we see, because we have a 0, a 1, and a 0, when we walk along this row, what that is going to have the effect of as we walk along the column is picking out only the second entry. And so when we walk along the first row, we pick out the second entry of every column, and that ends up putting the second row in the first row. The same thing applies in this second row. We have a 1 and a 0, 0. Walking down each column is going to pick out only the first entry, leaving 0 the rest. So the second row becomes 0, 2, 1. The third row of E, 0, 0, 1 is going to pick out the third entry of each column, giving us the third row. E times A gives exactly the same result as applying the row operation to A. E was generated by applying that same row operation to I. Addition of a scalar multiple. This is a very commonly used operation in Gaussian elimination. Really, the core eliminating steps use this operation. Identity matrix. What if we wanted to, say, subtract 3 times row 1 from row 3? Well, we would take row 3 minus 3 times row 1, 0 minus 3, 0 minus 0, 1 minus 0, gives negative 3, 0, 1 in the last row. The rest of the matrix looks exactly like I. This is our E. Applying the same operation to a matrix A, this is actually the result of the last row exchange step, as we might do to eliminate this entry as a step in Gaussian elimination. We would subtract 3 times the first row from this row. 3 minus 3 is 0, 2 minus 3 is negative 1, 0 minus 3 is negative 3. We have that entry here, and the other rows are unchanged. Multiplying this E by this A again gives us the same answer. What does this first row of E does? It picks out the first row, pick out the first entry of each column, so the first row is unchanged. The second row, 0, 1, 0, picks out only the second entry from each column. So the second row is unchanged. This third row, what does it do? It takes -3 times the first entry and adds it to the third entry. And so that, of course, achieves exactly the operation that we want. And you can work through the products and sums to verify this if you would like. Scalar multiplication. This is a quite easy one. Applying, say, the operation of half R2, scaling the second row by a half to the identity, would simply replace that second entry with a half for E. If we were to, let's do the same operation, replacing half of R2 with half of R2, not this addition of a scalar multiple here, to this matrix, scaling this row, 0, 1, half, as we have here. And if we apply this, multiply this elementary matrix by the matrix we have here, again, we get the same result. The first row, 1, 0, 0, picks off only the first element. The first entry is unchanged. The third row, 0, 0, 1, picks off only the last entry. So the last row is unchanged. The second row, it has 0 contribution from the first or last entries in each column, and has a half contribution from the second, which has the effect of scaling the middle row by half. So we see with these 3 examples that things are behaving exactly as we would hope. We can construct an elementary matrix by applying an operation to the identity. We can then use that to multiply by a matrix as a mechanism of achieving the row operation. Now, with that in place, we're ready to think about Gaussian elimination entirely done in the context of matrix multiplication. Now, I want to be a little bit clear. We are not actually going to do Gaussian elimination by creating matrices, elementary matrices, and then doing matrix multiplication in order to achieve the exchange. It's actually quicker if we're actually doing Gaussian elimination to just do the operations. But the connection to the elementary matrices is a very, very important conceptual step that we can imagine doing this matrix multiplication, and we are going to get some very interesting results here. So let's think about a full sequence of forward elimination steps. Right? And imagine that we have R of those, R individual elementary row operations that we need to apply in order to convert our starting matrix M into some row echelon upper triangular form that I'm going to call U. And we can represent this as a series of row operations that I'm calling RF1 for the forward step 1, RF2, RF3, and so on up to RFR, our whole sequence of steps. And we can sort of think about there being all of these intermediate matrices along the path as we manipulate our system, going from M, and we stop when we have our row echelon or upper triangular form. Right? This is just a sort of shorthand of the steps of Gaussian elimination, forward elimination. We know that each of these row operations can be achieved by doing multiplication. So instead of applying this row operation F1, we could multiply M by the corresponding elementary matrix, EF1. Instead of then applying row operation to that intermediate matrix, we could multiply by the corresponding elementary matrix, multiplying that by the result, so multiplying it by the answer that we got in the previous step, represented here, and continue along. As we do this, we multiply m on the left by EF1, and then multiply that on the left by EF2, and then on the left by EF3, and so on. And when we reach the end, when we reach our U form, what we have done is we've applied this whole series of multiplications, EF1, EF2, EF3, all the way to EF4. Right? We have transformed the row operations, the sequence of row operations of forward elimination, into a product of elementary matrices. We can simplify this notation instead of trying to write out all of these with product notation. This simply means, if you haven't seen this before, this is the multiplicative equivalent of a summation symbol of the sigma. This means start with I equals 0, going one by one until we reach R equals 0, and multiply all of those entries together. So multiply EFR times EFR minus 1 times EFR minus 2, and so on. And I have the ordering here so that this expands in the right direction, sort of with R on the left and 1 on the right. Okay. We can also conceptually simply replace this big product with another matrix. It's just a product of matrices. It gives another matrix, and call this F to represent the matrix representing forward elimination. And what then that gives is really all of these steps of Gaussian elimination can be encapsulated in one matrix F. F times M gives us our upper triangular form. Now what about if we continue with back substitution? We would start with U. We would take a sequence of row operations. These ones I'm calling B1, B2, B3 for back substitution, counting S of those, until we reach our reduced row echelon form, which I'll call R. In exactly the same way as for forward elimination, each of these steps can be replaced by multiplication by an elementary matrix. So the first row operation can be replaced by multiplying U by EB1. The second row operation can be replaced by multiplying that first product by EB2, and so on. And by the time we've reached our row echelon form, we've taken U and we've multiplied it by B1 on the left, then B2 on the left, then EB3 on the left, then all the way up to EBS on the very left-hand side. And in exactly the same way as we did for forward elimination, we can take this big sequence of this product of elementary matrices, represent it in product notation, and collapse that product of S individual elementary matrices into one matrix that we call B. B times U gives us our reduced row echelon form. We've managed to now really encapsulate forward substitution and back, forward elimination and back substitution into just two matrices, each of which is a product of elementary matrices. Now, we can stick this together to express all of Gaussian elimination into a matrix product. We have M taking a series of steps to our echelon or upper triangular form, another series of steps to our reduced row echelon form. F times M represents all those first steps. B times U represents all those second set of steps. B times F times M, or BF times M, gives us our reduced form. This product B times F is a matrix that does all of Gaussian elimination, forward elimination and back substitution to a reduced row echelon form. this is all still conceptual. At this point, the only way we know how to compute B and F is through this product of elementary matrices. But we are going to discover that there's a much simpler way to do that. Okay. Now, here's where the really interesting thing arises. Imagine that we were working with an augmented matrix of a non-singular square system. That is, M is A, B. Right? Well, we know a non-singular system, after we apply the Gaussian elimination, gives us a reduced row echelon form that has the identity in the coefficient block and the solution in the last column. We also know that we can get this reduced echelon form by multiplying BF, the matrices corresponding to Gaussian elimination, by M. Using our block matrix rule, BF times AB is BFA and BFB, but we know that this has to equal IX. So BF times A equals I, and X equals BF times B. But we've seen something very similar to this before. A inverse times A equals I. This is really the definition of a matrix inverse. BF times A equals I. The solution to a non-singular system. X equals A inverse times B. X equals BF times B. This product, BF, is the inverse of A. This product of the two matrices corresponding to back substitution and forward elimination, the product of all of the elementary matrices in the steps of Gaussian elimination, is the matrix inverse. Right? In many ways, Gaussian elimination is calculating the matrix inverse. They are the same thing for a non-singular square system. All right. This equivalence also lets us very easily derive a method for computing a matrix inverse. Let's just work with a slightly different block matrix. Consider the matrix where we have A in the first block and the identity in the next block. This is the same matrix we use to illustrate some ideas about elementary matrices. Gaussian elimination starts on the left and moves forward. And so just like we can add extra right-hand sides and perform Gaussian elimination and it doesn't change anything because it's driven by the variables, it's driven by the coefficient blocks, the same thing is true here. This I, because Gaussian elimination is driven by the coefficients, this doesn't change the steps of Gaussian elimination in any way. So our reduced echelon form, B times F times M, encapsulating Gaussian elimination in this matrix product, is a block matrix BFA and BFI. Right? But we also know that this first block will become the identity matrix. BFA is going to equal I. BFI, on the other hand, is just BF. Identity matrix multiplied by anything is the same matrix. And we already know that BF equals the inverse. What we see here then is that if we start with AI, apply forward elimination until we get our upper triangular form and something in the other block, and continue doing back substitution until we get our identity matrix here, we end up with the inverse here. Okay? Sorry, this sentence seems to be incomplete here. I'll correct that in the slides. It's just summarizing what we've said in words here. Okay. Now, so let's summarize what we've figured out here. If we start with a left block of A and a right block of I, and we transform through forward elimination and back substitution until we get a left-hand block of I, the right-hand block will contain the matrix inverse. This is now a nice, easy way to calculate a matrix inverse. We simply construct this matrix and go through Gaussian elimination. Once we have an identity, we have the inverse in the next block. All right? There are some checks we can make along the way. If a 0 row ever appears in this left-hand block during this process, that means we're not going to end up with I because we have a 0 row in there. As soon as that happens, we can recognize that A must be singular and has no inverse. We can stop at that point. There's no point in continuing if we know there's no inverse. Two things to keep in mind, mistakes that sometimes people make. In this context, A is the coefficient matrix, not the augmented matrix. Do not include a right-hand side in this construction of our starting matrix. Also, this only works for a square matrix. A non-square matrix can't have an inverse, so we can't use the same approach. And the size of I that we use has to be exactly the same size as A. So A and I have to be exactly the same size. Keep note of these couple little things. Okay. That almost wraps up the discussion, but I want to end here with just a little bit more conceptual discussion of what do we mean by a singular matrix. What is a singular matrix? When does a inverse not exist? What does it mean when a inverse doesn't exist? You will often hear me say, and other people say, that most square matrices are non-singular. What we really mean by that is if you randomly generate matrices with any real numbers, the vast majority of them will be non-singular matrices. Why is this? We can think of this from two different perspectives. From the row picture, a square system is n different hyperplanes in an n-dimensional space, 2 lines in 2-dimensional space, 3 planes in 3-dimensional space. The coefficients in the coefficient matrix represent their orientation, the slope of a line, the sort of the angle that a plane sits on in 3D space, and so on. And the right-hand sides just correspond to the offsets, like the y-intercept in 2D and so on. Right? And if you just think about the simple 2D case, if you have 2 lines in 2D, the vast majority of 2 lines in 2D intersect at a single point. There is usually a single unique solution for 2 lines in 2 dimensions. The only time there isn't is if there's a special relationship between those 2 lines. In fact, they have to be parallel. The same thing is true in 3 dimensions. Usually 3 planes in 3 dimensions will intersect at a single point. The only time they won't is if 2 of the planes are parallel or there's some other relationship between them. The relationship that actually breaks this is what leads to singular matrices. If 2 rows of a matrix are identical, related by a scalar multiple, then the matrix has to be singular. That would correspond to a case where you have parallel lines, parallel planes. Right? Similarly, if 1 row is a linear combination of the others, the matrix also must be singular. The planes aren't necessarily parallel, but one of them is simply a linear combination of the others. It's not an independent plane. Of course, if any row is 0, the matrix must also be singular. Fundamentally, singularity from the row picture means that these the system of planes or system of hyperplanes have linear dependence among them. They're not truly independent planes. We can also think about this same idea from the column picture. From the column picture, each column is a vector in an n-dimensional space. And for a square coefficient matrix, we have n of those. We'd like to take their linear combinations and see, can we make a linear combination for a vector on the right-hand side? This is 2 vectors in 2 dimensions, 3 vectors in 3 dimensions, and so on. Now, usually, if we have 2 vectors in 2 dimensions, the majority of 2 vectors in 2 dimensions, we can use to construct any other vector. The set of all linear combinations of 2 vectors in 2 dimensions is all of 2-dimensional space, unless those vectors happen to be right on top of each other or parallel. Right? Similarly, usually 3 vectors in 3 dimensions can be used to construct any other vector in 3 dimensions. There's a unique solution for most 3 vectors in 3D, for most n vectors in ND. What breaks this, again, are really the same sorts of rules. If 2 columns are the same, if 2 columns are simply scalar multiples of one another, then we have 2 vectors that are right on top of each other. They're parallel. That's one of the special cases that now breaks actually having n independent vectors. It will make some linear combinations degenerate, that there will be many answers, and others there won't be an answer. The system is singular. Similarly, if one column is already a linear combination of the others, then that doesn't contribute anything more to being able to generate linear combinations. The matrix is singular. And if any column is 0, the matrix must be singular, because again, that column doesn't give any information. What we see is, what is a singular matrix? A singular matrix is one that has rows and or columns that are linear combinations of other rows or columns, respectively. And actually, one of the very deep things about linear algebra and matrices that is not at all obvious to most people, but is true and underlies a lot of what we do, we'll be getting into this a little bit more later in this semester, is actually both of these things have to be true. If one column is a linear combination of other columns in a square matrix, then a row also has to be a linear combination of other rows. And we'll dig into that piece later. That's it for the conceptual discussions for Unit 4 on the matrix inverse. In the accompanying videos, we'll go through first just some general worked examples computing matrix inverses, and then in a second video, some applications to problems where computing it in matrix inverse helps us in solving the problem. Thank you, and goodbye.